Now, since n approaching infinity is the only possible limit concept for a sequence, we have some notational simplifications and some other things that I want to put together. So let me say notations and remarks. So first of all, since limit n approaching infinity an is the only limit concept a sequence can have, that is, n can only go to infinity, we usually do not write it. We usually omit n goes to infinity and write limit n. It will be understood that n goes to infinity. Okay. Secondly, because the limit definition of n approaching infinity, limit of an, is exactly the same as in the definition of the limit of a continuous variable, a real variable x going to infinity for a function f of x, okay, the related limit theorems are all valid. That's to say, since the definition of limit an is directly taken from limit x going to infinity f of x for a continuous variable x, for a function of a continuous variable x. Okay. The limit theorems are valid for sequences as well. Okay. What I mean by that is the following. Okay. Namely, the algebraic operations are valid. For example, okay, if limit of an is a and limit of bn is b, then okay, limit of an plus bn would be a plus b. Okay, limit of c times an would be c times a, or limit of an times bn would be ab, or limit of an divided by bn would be a over b. Both limits exist, but of course we cannot divide by 0, so we should say b is not 0. So all of these properties still hold for sequences. Actually, we have more than that, which is very important in dealing with limits of sequences. Okay, we have a 5. Namely, the squeezing theorem is valid. Okay. Let us recall what it said. Okay. Recall that if an is bounded by a Cn and by a Bn, and limit of an is the same as limit of Bn, which is L, then, okay, limit of Cn exists and it is n. Okay, this was a squeezing theorem. For sequences, this version is still valid. Now, with one modification, if An, Cn, and Bn are ordered this way, but not for every n. Okay. If it's true after some n, since n will go to infinity, it's still valid. So, let me say here that, okay, if the inequality or the inequalities, okay, this is valid not for every n, but is valid ultimately okay, this means there is an n0 and it is true for all n after that. Okay? Then the conclusion is still true. Okay. Now, because in the limit n will go to infinity, it's not important what the first terms do. Okay, we look at what happens if n is larger and larger. So this argument is still valid if it's ultimately true. That is, if the inequality is true after some n0. This is still all right. Now, the squeezing theorem is very important, as we will see in the coming examples that we will have. A last thing I want to say here is, right, the big three, continuing the properties. What do I want to say here is that if the limit is not a finite number, okay, then we can modify the definition accordingly, as in the case of a real variable function. So, if L is infinity or L is minus infinity, then, okay, similar to limit x approaching infinity, f of x is infinity or minus infinity, okay, we can modify our definition. For the sequence. Okay. So, okay, what this means is the following. For instance, if L is infinity, okay, you want x to be a large number, but you also want f of x to be a large number. So it means that, okay, instead of for all epsilon, there's a delta business, you have for all m, there is an m, for all m, there is an n, so that if n is large enough, then the value of f of x will be bigger than this m. So it will get nearer and nearer to infinity. For that, just recall the definition of this. I will not rewrite it. Okay. So even this is possible for a sequence. Now, if you remember, we had a theorem about a general real variable function which has a limit. If a function has a limit, then it was bounded for points near x0. So let me remind you of that property. Recall the theorem. Okay, for a function reals into reals. this was the following theorem. If limit x approaching x0, or infinity, it doesn't matter, okay, f of x, because this is what we need, is L, then, that is, if the limit when x goes to infinity, the limit of f exists as a number, okay, then f must be bounded after some point. Then f is bounded for x bigger than x0 for some fixed x0. Okay. Well, the idea, obviously, is the following. I will not rewrite it. Well, if you have an L here, and if your function goes to this L when x is pushed towards infinity, okay, then the values of your function cannot go to infinities or minus infinities. It must be bound in a strip. When? After some x0. Because we have no idea what the function does for small values, and we don't care. It may happen that the function maybe is like this. So it's not bounded near 0. But we don't care about 0. We care about very large x's. So it will be bounded between two values after some point on. Now, the same is true for a sequence. Let me state that. Similarly, for a sequence an, okay, we have the theorem that if limit an exists, then, well, for a sequence, such a thing cannot happen. That's to say, before x0 or n0, a sequence has only finitely many values. So they don't have a chance to go to minus infinity or plus infinity. Certainly they are bounded. So we don't have to separate at a point. We can directly say that the sequence is bounded. That is, there's an m for every n. Absolute an is less than or equal to that m. Okay. And finally, okay, terminology. Okay, if limit an exists, then one says the sequence is convergent. Okay. Okay. And if it does not exist, and if the limit does not exist, then one says the sequence an is divergent. Okay, the terms convergent and divergent are used for sequences and series, as we will see later. And one doesn't always say limit an exists. One simply says sequence is convergent. This is a terminology that is used in the literature. Okay. Now, let us consider some examples on finding the limits of sequences. So, okay. First of all, okay, sequences can have very different forms, unlike the functions of real variables we already know. But in many cases, the expression for the sequence comes from a real valued function with a real variable. So, firstly, we have the following obvious theorem, which will be of great help for us. Well, given a sequence, okay, and if there is a function of real values such that f of n is an, then one has the following. Limit of this f of x is L implies that limit of an is L. Now, the logic behind this theorem is the following. Let this be the limit. Okay. We have a function with real values, with real variable. So, perhaps it goes like this. Okay. This is my favorite sketch for such a function. It need not be increasing or decreasing. Okay. Its limit is L when x goes to infinity, as we see from this picture. Now, what is an? An is f of n. So, we look at the value 1. So, this is a1. We look at the value 2. So, we are here, it's a2, which is f of 2. And we look at 3. So, we get here a3. And somewhere we have n, and we get here an, which is f of n. Now, if the curve, okay, gets closer and closer to this horizontal line, the points we choose on this curve certainly are nearer and nearer to L eventually. So this is the explaining picture. So as f of x gets nearer and nearer to L, if we replace x with n, the same thing should hold. In case then the sequence comes from a function which has a real variable, it's enough to look at this limit. Okay. Let us see some examples. Let us look at limit of n over e to the n. The sequence is n divided by e to the n. Now, we observe that this comes from the function from reals into reals defined by f of x is x over e to the x. If you replace x with n, it's the same as f of n, which means that we can use the theorem if we calculate the limit of this function when x goes to infinity. So, okay, calculate limit x over e to the x when x goes to infinity. Now, because x is a real variable, and this is an infinity over infinity form, we apply L'Hopital's rule and check that we have x approaching infinity, 1 over e to the x, whose limit is 0. Okay, so by theorem, limit of n over e to the n is 0. Okay. Well, a remark here. Okay. Note that we could not use L'Hopital's rule for the sequence directly. Okay. Since there is no L'Hopital's rule for sequences, okay, limit n over e to the n, which is limit the derivative of n divided by the derivative of e to the n, which is limit 1 over e to the n, which is 0, okay, is not a valid argument. Since, okay, sequences don't have derivatives. So there is no L'Hopital's rule for sequences, so you cannot do this directly. But if you have a real variable, yes, you can do it, as we learned from the previous course. As a second example, consider the sequence minus 1 to the n divided by n. Now this sequence, okay, that is minus 1 to the n over n, does not come from a function reals into reals, since, okay, f of x minus 1 to the x divided by x is not defined. Okay? For example, if x is 1/2, well, we will choose x larger and larger. So if x is, say, 1/2 plus a very large number, etc. Okay. Well, of course, one can argue that this need not be the function. There can be more complicated functions whose value at n is exactly this. Okay, it's possible. Okay, but for practical reasons, this is the first function that comes to our mind, and clearly it doesn't work. This means that the theorem cannot be used. Because there's no such an f. At least practically, not a nice f is not present. Since we cannot use this theorem, okay, we can go back to our previous arguments. That is, we can try to use the squeezing theorem. Okay, let us say instead use the squeezing theorem. Okay, this is quite easy because an is minus 1 to the n over n, and certainly it's always less than 1 over n. In fact, if n is even, they are equal. If not, this is negative, this is positive, so it holds. And it's always greater than minus 1 over n. Now, in this formulation, we can easily show that 1 over n goes to 0 when n goes to infinity. Similarly, minus 1 over n goes to 0 as n goes to infinity. So by squeeze theorem, this goes to 0 as well. Okay, this is allowed. We can use the squeezing theorem. But using the squeezing theorem is not always very easy. We have to work a little bit harder sometimes. As a third example, let us consider the limit of, say, 5 to the n divided by n factorial. Now, here we have the same problem as we had in the second example. Namely, for an arbitrary real number. Okay, this is not defined because x factorial is defined only for integers. It's also defined for 0, not a negative integer, but for positive integers or 0. So this expression does not come from a real variable function, which means that we cannot use the theorem. So we don't have that simplicity all the time. Okay. But instead, we can use the squeezing theorem. Okay. Let us look at 5 to the n over n factorial. Now, how many 5s do we have here? Certainly n many. They are multiplied. At the bottom, we have also a multiplication of n numbers. So let us match them together. So this is 5, 5, 5, 5. Okay, n of them. At the bottom, I have 1, 2, 3, 4, 5, and n minus 1, and n. I multiply the first n integers, positive integers, and so it's exactly that. Now, when I look at this ratio, okay, I see that it is 5 to the 5 divided by 5 factorial. I could have done it with 4, okay, which takes care of the first 5 terms. Okay, it's exactly equal to this. Now the others are 5 over 6, 5 over 7, up to 5 over n minus 1, okay, which is bounded by 5 to the 5th power, 5 factorial. Now, all of these terms are smaller than 1. So it happens that I have the inequality 5 to the 5 over 5 factorial times 5 over n. This is a constant divided by n. It dominates the given n. On the other hand, okay, this is positive. So its limit will be 0 when n goes to infinity. This limit, a constant divided by n, goes to 0 when n goes to infinity. And the middle term, by squeezing theorem, okay, should go to 0. If you preferred to use the definition directly, this would be exactly the same process you would do, but you would modify it with an epsilon and n0. I will not go into that. Okay. For any real number, show that this limit is always 0. Okay. Here, if k is a positive real number, you can use this approach. If not, you take the absolute value. Okay. You can also show that the limit of any power of n, okay, divided by some m to the n, m greater than 1, okay, is 0 for all k. R for all m greater than 1. Well, this tells us basically that the factorial growth, if this goes to infinity, well, if k is positive, this also goes to infinity, if k is a big number. But the factorial goes to infinity much faster than the exponential. And this tells us that the exponential goes to infinity much faster than a polynomial. So this is a comparison of the rates of going to infinity. Okay. Obviously, to make sense, you should change these things, for instance, in the second case, to a real variable. But you cannot do it in the first case, but you can imitate this proof. Okay. Well, Now we said that a sequence is a function of n. So, any function of n is considered a sequence, and this tells us what the term an is, explicitly. That is, as in these examples, an is 5 to the n divided by n factorial. So we know the expression. But because of the nature of the definition of a sequence heavily depends on natural numbers, because its domain is natural numbers. But natural numbers have the basic property of counting. That is, they can be counted, and there's always a next term. Now, when we talk about the next term, we recall the logical proof method of induction. Recall, induction says that if a statement is true for 1, and if it's true for n, it's true for the next term, then it will be true for every n. Now, because of this, sequences can be defined inductively. What does inductive definition mean then? It means that you define it for 1, and then you state a rule which says that you can get the next term once you know the one before it. So, I will not continue with a formal definition here, but directly go to examples. The first example is that a1 is 1, and an is n minus 1 over n, n minus 1, if n is greater than 1. Now, this is an inductive definition, because it says what a1 is, and if you know an minus 1, it tells you how to get an. The problem with inductive definitions is that you do not know what an is actually. Explicitly, you don't know it. However, the advantage is that you can prove some properties just by looking at it. For example, n minus 1 over n is always less than 1. So this says an is always less than or strictly less than the one before it. So it's a decreasing sequence, and so on. And the second advantage is, in many cases, it's easy to formulate this instead of finding the general term. So let us try to find an explicitly. What is it? To do this, let us check a few values. a1 is 1. That's given. a2, now 2 is bigger than 1, so I can put 2 in this equation. It is then 2 minus 1 over 2, a2 minus 1, which is 1 over 2 times 1. If we check the next term, a3, this would be 3 minus 1 over 3, the previous one, 3 minus 1. So it is 2 over 3 times a2, but we found a2 to be 1 over 2, so this is 1 over 3. Now, when you look at these terms, you have an educated guess. Okay. You have a guess which says that A1 looks like 1 over 1, A2 is 1 over 2, A3 is 1 over 3. So AN should be 1 over n. Now, this is not AN yet, it's a guess. So, this is our guess. It needs to be proven. Now, if the sequence is defined inductively, guess how you would prove it, certainly by using induction. Okay, use induction. For 1, A1 is 1 over 1. Is it true? Yes. A1 is 1. Okay. If true for K, if AK is 1 over K, then the next term, AK plus 1, now we go to the defining inductive equation. That would be, okay, remember, instead of n, you put K plus 1. Okay? So K plus 1 minus 1 divided by K plus 1, AK. But AK was 1 over K. And, okay, 1 over K cancels with the K upstairs. And so you have 1 over K plus 1. So the formula is correct for the next term. Conclusion, AK is 1 over K for all K by induction. Okay, so this is another way of characterizing the sequence AN is 1 over n. Okay. But finding AN is not always this simple. Okay. One can consider various examples here. For instance, let me consider this. Say A1 is 1, okay, and n is the square root of 1 plus a n minus 1. Now, okay, if you want to find the general term, you will have some difficulty here. Okay? But you can find any value a n if n is given to you, which means that to find an, you have to know all the values before it. Okay. So let us try to find them. A1 is 1. A2 would be square root of 1 plus A1, which happens to be 1. So it is square root of 2. Well, things are getting more complicated. A3 would be square root of 1 plus A2, which is root of 1 plus square root of 2. Well, it's getting more and more complicated. Or you can write it for simplicity in this form. Okay? And then you can guess that your an, not a very useful way of writing, but still it would be the root of 1 plus root of 1 plus root of, finally, plus root of 1 plus 1. Of course, in the 3 dots that you have here, you have lots of 1 plus square roots. Okay? So you can show it if you want this way. And so on. Well, this is a way of finding an, but it's not very useful. Okay. But there are worse cases. Okay. Define A1 to be 1. Define A2 to be 1. And for n strictly greater than 2, okay, an is the sum of the previous two terms. Okay. So the rule is to get an, add the two previous values. Well, it looks fairly easy. This is called a historically famous sequence. Because it has very interesting consequences in mathematics, in mathematical history. Okay, let us write down some values. Now, A3 is, because it's bigger than 2, it's the sum of the previous two, so it is 1 plus 1, so it's 2. A4 would be the sum of the last two, so it is 3. A5 would be the sum of the last two, so it would be 5. A6 would be the sum of the last two, and it continues like that. So, to find A100, okay, you need to know, okay, A99 and A98. You will add them. Okay. But to know A99, etc., etc., so one needs to know all of A1, A2, A99. Of course, this is not practical at all. Well, it would be nice if we knew what an is. Explicitly means in open form as a function of n. Okay. So we will put n equal to 100, we will get the value. Now, this is possible, but not as easy as you might expect. I will not go into certainly a proof of this, but I will just give you the answer. Okay. It's true if n is 1, 2, etc. You can check that A1 is 1, A2 is 1. If you are not tired, you can check A3 is 2, just to have a simple check. Okay. Well, for 1 and 2, it's rather easy. For 3, you have to work a little bit, and not too bad, and so on. So this example shows that the inductive definition can be much more appropriate, simpler, than the general term itself. Clearly, you would not like to work with this AN, okay, in this form. And it's easier to determine the values of the sequence using the rule. The rule is add the last two. Okay. It's simple, but the general term is quite difficult. Incidentally, this argument has been quite useful in the theory of difference equations, which is similar to differential equations in the continuous variable case.